I'm going to conclude my remarks for this lesson by laying out a little bit what the game plan is going to be in the following lesson, and indeed as we talk about how statistics can give us some idea about the states of a molecule, states of molecules in a system, so that we can learn something about their macroscopic properties. So just to review, what we've learned up to this point is that the energy of a molecule can be written with several different contributions. So for example, it has a contribution from its translational levels, it has a contribution from its rotational levels, has a contribution from its vibrational levels, and even a contribution from its electrons and its electronic levels. So we have a lot of different ways that we can place energy into a molecule, because we can place some amount of it into translation, we can place a different amount into rotation, yet a different amount into vibration, and probably not very large amount, but we can place some in electronics as well. I'll remind you that what we've learned about the relative magnitudes of these different energies is that electronic energy levels are spaced the farthest apart, and they're greater in spacing than the vibrational levels. The vibrational levels are about 100 times larger than the rotational energy levels are spaced apart. And then the translational levels are really close together compared to all of these, and many orders of magnitude more of them than there are of some of the others. Now, I also know that there are different quantum numbers that I can ascribe to each of these different types of motion. So we saw that we had nx and y and z for translational motion. We had j. There's also others that we can use for rotation. For the vibrations, I can have the quantum numbers for each of the different oscillators up to v of 3n minus 6. And for the electronic, we don't even worry about the quantum numbers there, but there are quantum numbers here as well. So there's lots of ways that I can use these things to label the state that I'm in. So we'll think of these things as being something akin to state labels, so we know sort of what states we're talking about. Now, how can I organize this? How can I create something that will allow me to systematically talk about how the molecules are distributed among these different energy levels? Well, first of all, I might create a list, and I'll tell you that practically speaking you couldn't do this, but let's suppose you started a list where you took the very lowest molecular energy level, and I'm going to use sort of a Greek sigma to denote molecular energy levels. I'm going to put the very lowest one here, and then the next lowest one here, and the next lowest one here, and go ahead and build up until I get to, say, the jth energy level, and keep on building up until I ultimately have an energy level that is the total number of energy levels that are available here. Now this n, I probably shouldn't use n. Let me use a different, let me use m as the total number here, because this m is going to be a huge number by and large, because we have so many translational levels contributing to this, and a lot of rotational levels as well. So when we begin to add all of these up, we're going to find in fact that there are many, many more energy levels available than there are even molecules in our system. In fact, each molecule will have its pick, basically, of any energy levels it wants to choose. But in terms of organizing, let's just say I'm organizing things this way, where I'm going to list each of the energy levels that are possible in this molecule. Now, each of those energy levels is going to have associated with it a particular degeneracy. So remember I mentioned the word degeneracy before when we talked about rotations, and the degeneracy is just basically the number of states with the same energy. So if I talk about the degeneracy of each of these states, I'm going to give it a number, I'm going to give it a symbol, I'm going to call it G. So G1 is the number of states that have energy level E1. G2 have energy level E2, G3 for that. For the jth energy level, it'll be G sub j, and of course for the highest energy level, if there's really not a highest level, but it'll be some huge number. All right, where does this degeneracy come from? Well, we've seen already in the case of rotations that if I have a rotational state with a quantum number j, that it has an intrinsic degeneracy of 2j plus 1. And certainly that contributes to the overall degeneracy, but these degeneracies are something a little bit different. If you think about how many translational levels are packed in there, and if I add different amounts of translational energy to different amounts of rotation, vibration, and electronic, for a particular energy level, let's say this one, there's many different ways I could construct a molecular energy of this magnitude by partitioning it into these various types of energy. There's, like I said, electronic is probably just going to be one. Maybe vibration is just going to be one, but there's lots of rotation levels and millions and millions and millions of translational levels that I can pack these in. So it will turn out that these degeneracies are effectively, and I'll call it effective degeneracies, are very large. Effective degeneracy, very large. In fact, in general, we'll be able to say that this degeneracy is so large that it's going to be rare to find more than one molecule in a particular state that is labeled by that degeneracy. All right, now the last step I want to do in organizing my system is I want to specify how many molecules are in each of these energy states. So I may say that there's N1 molecules in the first state, and there's N2 molecules in the second state, and N3 in the third, and so forth, and up to Nj in the jth state, and keep on going N sub m in the highest state, if there is a highest state. All right, so basically these numbers are going to specify how many molecules have each of these energies and which states they're in. So this is specifying something, specifying how the molecules occupy the different quantum states. So in other words, this is, in fact, the most information I could have about this system. You know, I know what state each molecule is in. I know how many molecules are occupying that energy state. There's not much more I could know about this system. Well, perhaps there is more, but I'll just say that as far as we go, as far as chemists go, that's about as much information as you can get on a particular system. So by knowing these numbers, I'm basically specifying something, intrinsic about the system that is quite unique. So I'm going to wrap these into curly brackets and list them as though I am able to list them, because I'm going to have, you know, literally 10 to the 23rd or 10 to the 30th or 10 to the 40th different of these numbers. So there's no way I could actually physically construct this list, but this is a thought experiment for now. But this list of numbers is going to describe a distribution. Okay, a distribution is simply telling me how many molecules have each of these energies. All right, now as a distribution, I mean, we can think of this as, you know, what is the distribution of people in different schools or different classes? And it would be the number of students in each class. Okay, but if the classes could be infinitely large, then we could have some distributions where all of the students are in the same class. Or we could have distributions where there's one student in each class and there are just as many classes as there are students. Okay, so this is the sense in which we're creating this distribution. Now I'm going to have a special name for this. I'm going to call this a macrostate. And this macro state is something that really helps us define something about the system and define the way that that system is put together. Now, I'm also going to care, though, because of these degeneracies that I have in each of the energy levels here, it's going to define for me, for a given distribution, a number of different ways that I can equivalently create this distribution. So, for example, if my degeneracy, you know, is 1,000, so let's say for a particular state, G sub j, it's 1,000, and I've got 3 molecules in there, well, there's a whole bunch of different ways that I could distribute 3 molecules among 1,000 possible states, even though they would all have the same energy level, E sub j. So this number of ways, so the ways that I can distribute, or ways that I can parcel out Nj molecules among the states that comprise energy level Ej, that number is huge, and it represents something that I'll call the number of microstates for that given occupation. So now the number of microstates for that particular one, let's call that W sub j. The total number of microstates for the distribution is going to be the product of all of these Wj's. So the total number of microstates is going to be W1 times W2 times W3 all the way up to Wj and beyond. So it's going to be a huge number of different microstates, typically speaking. So what is our game plan for all of this? How are we going to make sense of labeling a system this way and describing it? Well, the game plan is actually pretty simple, because what we're going to do is we're going to look for the distribution that has the most microstates. So the distribution with the most microstates is inherently going to be the one that is the most important. Why do I say that? Well, it turns out that we're going to make an assumption that all of the microstates are equally probable. And this is important. We're not going to give any preference to one microstate over another. We're going to say that they're all equally important and equally probable. So that means that the distribution that has the greatest number of microstates is in effect going to be the most probable distribution. So the most probable distribution is going to be the one with the most microstates. So our game plan is going to look something like this. We're going to first assess various possible distributions for our system. So assess and construct the possible distributions. This sounds like an impossible task because in fact there's a really great number of them for large systems, but we're going to work with smaller systems first to see how this works in principle. We're then going to evaluate for each of these distributions the number of possible microstates. So evaluate the total number of microstates for each distribution. We're going to make this assumption that microstates are equally probable. And finally, we're going to say that the most probable distribution is the one with the most microstates. And this is going to be the one that will prove to be of paramount importance in discussing what state the system might be in. And in fact, I'll spoil this a little bit and say that the one with the most probable distribution, the one with the most microstates, is going to turn out to have so many more microstates than the next most probable distribution that in fact it is the only distribution that we will need to worry about. So the whole game plan here is to find that most probable distribution, because once we found it, we'll be golden. We'll know exactly what state the system is in. We'll know exactly how to characterize that system and how to calculate its macroscopic variables and macroscopic properties.